So hello and welcome again to my live coding stream. Last week I started creating a GIF decoder using web technologies, basically just JavaScript at this point. And we got so far with decoding the data. Turns out GIF is one of those formats that has a section at the top of the file for applications to stick in just whatever data that they want. And the GIF that I have been using for testing has that. It has a bunch of data in the application-specific section. And we basically just had to work through skipping over that, even though we didn't care about it. So where did we get to? Let me switch views. You can see my desktop. So here's the code from last time. It is just a bit less than 200 bytes, 200 lines of actual code. DevTools are open. You know, we're outputting a bunch of stuff. So nothing particularly exciting here. It's just some data. We haven't got to the meat of the application yet. We read the global color table, so our palette of colors that we're going to be using to actually draw the image, but we haven't actually got to it yet. The last thing we got to was, so in my code, I go through and basically you say, okay, each GIF file begins with a header, and it has a logical screen descriptor. If the logical screen descriptor says we should have a global color table, then that will be next. And then we've just got some data, and we just keep going, reading things until we get to what's known in the spec as a trailer, which is a data section with a length of 0. So not just a length of 0, it actually has a specific marker to say that it is the trailer. Beg your pardon. Now, so far what we've been doing is just I've just been following the spec, reading data, and just bunging things into properties of my class, just saving them all for later. We haven't really considered what any of it means. I just want to get some data, and after we've started parsing the file, then we'll be able to look at what it actually means, what any of this data can be used for. So we managed to get the width and the height of the screen, and that is good. That is our first. That's the first thing that we could actually use to change the display of the image. You know, we can get our canvas and we can size it correctly. That's great, but we don't have anything else. We don't actually have any of the image data. Now, where we got to is in this parse data. There are, other than a trailer, there are 3 things that we could get. We could get what's known in the spec as an extension, whatever that means. We can get an image descriptor, or we can get junk. And where we got to is that in our test GIF, we had got to an error, not yet implemented image descriptor. So we've got here, the next thing that's parsed in our file is an image descriptor, and we haven't written any code to do that yet. You can see that in the extensions, we put in cases for other extensions that we don't yet implement. So we've got some not yet implemented errors in there. So anytime we get to a part of the file that we're not dealing with yet, we should get told about it. Or an error will happen, and we'll be able to, and that'll tell us what we're going to work on next. But before we get to that, I wanted to talk a little bit about. I just sort of dived in last week. I want to talk a little bit about the philosophy that I use when I'm coding this sort of thing. And that is, there's very little point in designing code for this sort of thing, I generally think that most projects you don't okay, for a lot of projects, designing things up front isn't actually worth it. Not designing the code. Obviously, you should design your application. You should decide what you want it to do, so that you know what you're working towards. You can put in screen layouts and what the buttons will do and what the functionality will be. The actual code, there's not much point in writing a description of that. This is my view, and I know that other people may not agree. But the only really accurate description of how your program works is the code. So designing the program is writing it. That's my philosophy here. So because I can't really know how the program should be laid out until I've been writing it, I don't worry about it. I write out code that works, that will do roughly the correct thing, and I don't really worry about I don't particularly worry about efficiency or how things are stored or what order I do things in or whether it's in one file or multiple files until I've got a bit further in, and then I can see, oh, well, this is clearly a much better way to do this thing. Now we have one of those now. Where last week I said that, so basically what I do is I get the file using fetch, and I get an array buffer for it, and then my GIF, I just pass in that buffer. So it's just a big blob of bunch of memory with all the information from the file in it. And then as we go through, I'm basically just creating, I'm holding a position, which starts at 0 at the beginning of the file, and I'm creating new uint8 arrays, or potentially other kinds of they're called typed arrays. I'm just saying, hey, use the buffer, but and use the current position, and then here's how many bytes. And I'm just getting a ton of these arrays. Oh yeah, there's uint16 array. And I kept saying during the stream that I knew this was bad, but I couldn't really think what the correct way of doing it was. And literally 2 minutes after the stream ended, and I wasn't having to talk through everything, and I was able to think a bit more clearly, it struck me, and I worked out what I should be doing. Now, the reason why I was using holding onto this position and using that all the way through is because I've written code before. I was parsing a programming language, and you pause along and you look to see what the next thing is, and you might read through to a certain amount of data before you realize, oh no, it's not this thing, it must be something else, and you have to rewind. So you pass in the current position, you read through, and then when you decide, actually, this isn't the right thing, you just return the position to what it was when you started, and then return up, and then you try the next thing. GIF is just not that complicated. GIF, we can tell at any given time what the next thing should be, or a range of things it should be, so that in here where we have, we read a label, and then it's definitely going to be one of these things, and we can tell just by looking at one more byte. We read the label, we know it is a label, and then we can tell just by looking at the label what the next thing to read is. There's never any guesswork, there's never any going backwards in the stream. So, a better way to do this will be to treat the stream as an opaque thing. Just say, give me the next byte, or 16-bit integer, or string of this such and such a length. And just take things off the stream one at a time. And then we have to maintain position somewhere, but we're not creating these arrays all over the place. We're not having to maintain position in the file as part of our GIF. We can abstract that out into something else. And then, so here, instead of saying, new uint8 array, blah, I'm just going to say const label equals reader.getByte, or something like that. I'm just going to say, hey, whatever I'm using to read this stream, give me a byte from it. And that will come in very handy later on when we do LZW decompression, when we need to say, hey, give me 3 bits, which is much harder to do with a uint array. Your position is going to end up being not an integer. Oh, hey, this room, the light is going out because it thinks there's no one in here. Okay, sorry about that. So what I'm going to do is I'm going to create a new class to handle that streaming. And I don't really know what to call it, but I'm going to call it a response reader because it's what I'm going to use to read the response that I got. So it's a response reader. And in its constructor, I'm going to take in a response. Or do I want to take in a buffer? You know, I'm going to make this. I've already changed my mind. It's going to be a buffer reader. And here we're going to take in the buffer. So buffer equals buffer. And then we're also going to have to maintain that position. But it will be in a separate class just for reading things. So then, well, what methods does this thing need to have? I'm not really sure. So here we go. This.reader equals new buffer reader. Buffer. I'm just going to go through and start adding calls to this class throughout the code I've already got, and then that will tell me what calls I need to have in. It seems pretty simple. So here, this is going to be this.reader.get. We're getting an array of 10 bytes. This is just to sort of peek ahead and see what there is. There shouldn't be anything here. Because we are going through all the way to the trailer now, actually we can remove this. This should never get called. We can check that we actually reached the end of the stream. I mean, the GIF format is possible that once you reach the end, you've got the trailer, that it's valid to just have a bunch of data afterwards, in which case we shouldn't check that, but nonetheless I should make sure that that's the case before ignoring it, because if we get to what we think is the end of the file and we're only halfway through reading through the bytes, then we'll probably have a bug. So I would like to check this case. What do we got? So const byte equals, this is going to be this.reader.get. I'm going to say, okay, read byte. And we don't have to pass anything to it, just reading a byte. And the reader knows where we are, the reader knows. I am immediately scoping myself here because the trailer, the way I'm detecting the trailer is that I am reading ahead 1 byte. Do I do this anywhere else? If I don't do it anywhere else, then it's very easy to work around. I can very, very slightly change what I'm doing. No, I don't know anywhere else. Okay, good. So when we parse data, I'm just going to change the code for parse data. So that it's also going to look for a trailer. So it's going to be else if first byte equals not x3b. What was not x3b? Semicolon. Oops. And this is the trailer. And in this case, this lets me know that it's time to end. So what I'm going to do is I'm going to return false from here, return true any other time. So we can get rid of that. And then in here, I'll just do while this.parse data. With no body. Just keep parsing data until we reach the end. Okay. So header bytes, that's going to be this.reader.get read byte array. This one we really do want an array, and we want 6 values. 6. We can still abstract it away a little bit. I need to turn on word wrap so we don't have code disappearing off the edge of the screen. So here, we're going to say that width is this.reader.get u16, and then height is the next u16. We don't have to do that anymore. So background color index. Oops. Reader.get byte and these ones are all on byte 0, so extra, we'll continue calling it extra, is going to be this.get okay. Get byte. I've mixed get and read over and over and over again, haven't I? Yep. And I've accidentally deleted a bunch of code here. Yep. But instead of being extra 0, these are now just extra, because it's no longer an array. It's just the single byte that I actually want to process. So here, yeah, I give up. I keep using get instead of read, so clearly that's what the name of it should be. So this seems a bit cleaner to me. I don't need to maintain any of this position nonsense. Never have to update position here. This doesn't need to have a position. And it's just a bit clearer what I'm doing with things like this. I'm getting a byte and then testing it. Level color table. Okay, so this one is reader.get byte array of color table size. I don't need to update the position. First byte, this.reader.get byte. Don't need to update the position. go. That one's a byte. This one is a byte array. Get byte array. Sorry, how many was it? 8. This one's a get byte array of 3. No need to do that anymore. No need to do that. No need to do that. And I think this will reduce a lot of the places where I could have errors, where I was manually dealing with updating the position in every single function call. Now I'll be centralizing it all in my buffer reader class. This one's a byte. Let's get byte. This one's a byte. This is a byte. Oh, alright, okay, that one's a byte. This one's a uint 16. Nope. Got some colons there. This one's a byte. Hang on. Fields. Oops. Here. Position plus 1. Okay, so I need to read this in a slightly different order, otherwise it's going to go wrong. So I need to do fields here. Okay, that's fine. I can still replace this with create a get byte. Oops. And that's what this is. Uint array element 0. This one's a U16. U16 being a 16-bit unsigned integer. That one's a byte. And then these ones come from the fields. That. So now I just have to convert this code to build the results afterwards. So this code will instead build a bunch of local constants, and then we'll stick them all in an object at the end. I don't actually need fields in there. So here's some of my multi-cursor foo. I'll just transform this. So I'll take all of these local variables and put them into an object. Actually, no, let's try and lay this out a little bit more nicely on it. There we go. Now, obviously, this is not good yet. This lot need to be const. Fields is already a const. I all need to end with semicolon, and here at this point it needs to be space equals instead of a colon. Does this look right? So up here we've got block size, byte, good. Fields is a byte that we then parse more stuff from. Delay time is an unsigned, which we decided last week was an unsigned 16-bit integer. Transparent color index is another byte. Block terminator we're already dealing with. Or do I need to read that off? Okay, we may have some bugs if these things are expecting there to be a block terminator, which I was previously ignoring, because maybe I was just skipping past it in the stream by updating the position to be one higher than I'd actually read. So that might be that might be something to think about. Okay, I've just noticed that there's a whole bunch of stuff going on. Echo. Why do I have echo? Okay, so hopefully that has solved the echo. I do have two microphones here, and I don't know why. Okay. They're both the same microphone. It's just been added twice in the mixer. Weird. Cool. Sound is better. So yeah, I didn't notice the chat for a long time there, even though I moved it so that it was on the same screen that I'm looking at when I'm trying to see what I'm doing. The two makes that. Yeah. Okay, next Chrome Dev Summit. The Big Web Quiz, byte or not a byte? How do you do the multi-line select in VS Code? You can alt-click. That gives you well, okay. In the latest VS Code, it's actually in the latest VS Code, it's command click again, but in this version, it's still alt click, or at least you can set it to command click now, which is what it was in Sublime Text. You can also, if you've got a bunch of text selected, you can do Shift Alt I, and that gives you a cursor at the end of each line. What else we got? There's hang on, is it Command and Alt? So Command and Alt gives you a new cursor in the same position on the line below, so that you can select a whole bunch of new lines that way. And then obviously you've got Command D, which if you select some string, and then Command D selects the next occurrences of it, so I get all these consts, and I could turn them to lets if I wanted to, but I don't, because these things don't change. So let's use const. So yeah, I use multi-cursor all the time. It is the best thing about modern text editors. It's the only reason. I mean, honestly, when I started using Sublime Text editor I'd had before that barely did syntax highlighting, and I would not have moved to a proper modern text editor if it hadn't been for multi-cursor. It's the only good thing about modern text editors, in my opinion. So, well, okay. I mean, VS Code. I've moved to VS Code because it has some other nice features as well. Where was I before I was rudely interrupted? So now I should be making the same result object that I had before with all the same data, but I'm just having to pull these out separately so that this field gets pulled out in the right order, because I'll no longer be able to pick and choose where in the stream that I take things from. It will always be just whatever the next value is. So that's the price that I'm paying for a slightly cleaner way of dealing with it. And we're basically done. Just got a couple more. Got a byte here. Start.reader.get byte. And I've got an array here. Parse subblock. Where does this get called from? What is a subblock? Oh, we decided we didn't know and we didn't really care. It's part of the application extension. It's just some stuff that we'll probably never be able to parse, because it was up to some specific application to decide what it is. Is the plan to render the GIF in a canvas or something? Yes. I kind of hoped we'd get there last week, but it turns out there's a lot of junk in GIFs, and I didn't get there. So yes, there will be a canvas, and I'm hopeful that we'll get this today. Hopeful. So this I do need to either read this off. You know what, I'm not going to read this off. I really don't care. So what I'm going to do is I'm going to say this.reader.skip length. I don't care. I just don't care. We're not going to return anything from here. In fact, we don't need to put it in there. I'm going to read the length and then just skip. And that will update my position in my reader. Okay, so now I need to make this reader do something. So there's a bunch of places where I call into it and they don't exist. Now I don't have any code linting here, so I'm just going to have to kind of hoping to see the errors and it will tell me what I've done. Anyway, so get byte. So one of the ways we can do this is instead of just having the buffer, we can have what's called a data view. Okay, MSDN time. Yes. Typed array. What are the ways we can look at typed arrays? Array, data view. It was data view. Data view. One of the nice things about a data view is that it gives you get int 16, get uint 8, that kind of thing, and you just pass in the offset. So I will have my data view and I'll keep my position, and then I just get to call the underlying methods to do this. And this will be a lot easier than managing my own typed arrays all over the place. So this is a new data view, which takes a buffer. Offset, length, we're just going to leave them at whatever the size for the buffer is. So in here, I can say return this.dataview dot, what does this use? Reader, oh, they use get as well. Maybe that's why I kept wanting to use get. Get uint 8. This dot position. Sorry, this dot position plus plus. Let's refresh here, and it should error to tell me. Oh, why aren't you erroring? Should error to tell me that those functions don't exist. Can't even reliably break things. That's how bad things have gotten. Is this the right code? No, this code is not. Alright, so difficult to see. I've made everything, the text slightly bigger, or at least I thought I had. And normally I'd work across multiple like screens, multiple desktops. I'm finding it very hard to keep everything on the screen. But clearly this is not what I was looking at. So disable cache. Why are all these cancelled and pending? Give me a sec here. Let's have a look at my server. It's crashed. It's crashed? Well, that's great. But let's kill it with extreme prejudice. No, that's not doing it. 8,000. This may not be attached to my Cernbook. Oh, I'm revealing all the secrets here. Yeah. What is going on? Why is my server not working? There are stock jobs. Oh. Yeah, there are. I want to kill them. No, that's not working either. Oh, there we go. Let's just come out of the terminal. I apologize. This is not fun or interesting. So this is my stream folder. Let's run the server. Command not found. NVM. Yay! My nothing is appearing. Finally got my nothing back. Right, that can go away. Right, where were we? So I'm expecting this to error out to tell me that get byte array is not a function. Okay, and that is how I'm going to work out whilst implement get byte array. And this is going to have a length. So this one is going to return an array buffer. So result equals new int 8 array. And it's going to be this dot buffer at this dot position for length bytes. And here we are going to have to update the position plus equals length. And then return the result. But it should be about the only place that we now have to do that. So we won't have the bug in a bunch of different places. What else? Did we ever call anything else? I'll get you 16. Okay, so we actually need to do something slightly different here. So we will call this not with position plus plus because position needs to go up by 2. This is 16 because uint 16 takes up 2 bytes of position, and position is in bytes. How are we doing now? Get byte is not a function. No, that's because hang on. Get byte is not a function. This not this dot get byte. This dot get byte. That doesn't exist. It's this dot reader dot get byte. This dot reader dot skip. Okay, yeah. This one is very easy. Skip length. This dot position plus equals length. Boom. Cannot read property symbol iterator. What are we looping? We're not even looping over anything. Okay, so parse subblock no longer returns. I still need to return the size. Okay. Because the way that we tell when we've finished all the subblocks is that the size becomes 0. But we don't care about the data. Just don't care about the data. It's all junk. Oh yeah. There we go. So we should be back to unknown block type 0. Okay, I think this is that the byte at the end of the what do we say here? The block terminator. In the spec, I'm going to bet the block terminator. I'm willing to bet that's a 0. This 0 length data subblock is used to terminate a sequence of data subblocks. It contains a single byte in the position of the block size field and does not contain data. Contains the fixed value 0, 0. So here, I wasn't previously reading this. So at the end of here, I'm just going to say terminator equals this.reader.get byte, and we'll just confirm that it is a 0. If terminator is not equal to 0, then something went wrong. I don't know what. It'd be a bit of a mystery why that would be the case, but apparently, but we should check for it. We should check for it. Okay, so now we're back where we were. Not yet implemented. Image descriptor. Cool. So here, where we parse the various sections, where we parse data, image descriptor. So this is going to now say this.parse image descriptor. And this, I think, is where we start to get real data out. Some real data that we actually care about. I'm going to put this slightly higher up because this is more important than any of that extension stuff. Oh, this position can go away. Do I have any of those anywhere else? No. So what's the format of our image descriptor? First of all, I'm going to take away this, which is taking up a whole bunch of screen space. So in our spec here, if we find the image descriptor, color table, image descriptor. Here we go. We have some stuff that we need to parse. And now it should be a bit easier to actually parse this stuff because we have a better tool for doing that. So image separator. Separator. Need a linter for English. Equals this.reader get byte. And so we got byte, unsigned, 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 unsigned. So they're all at U16s. So why don't we let's use some multi-cursor magic on this lot. So we're going to get rid of these lines. Get a cursor on each line. These all happen to start with that, which makes me very happy. Get rid of those spaces. Get rid of those spaces. These all end with the word unsigned. So they're all this.reader.get U16. Magic. And then packed fields, we have 3, 4, 5, 6, 7, 8. They are 1 byte, 8 bits. So the packed. Get a reader. Oh, this reader get byte. No, typing too many things. How much do I care about this information so far? So you know what? Like, there's one thing I care about here. Ugh, stupid meeting room. Stupid meeting room. In fact, no, I don't care. I'm just going to return an object which is all of these things. So we copy those, stick those in there. So what do we actually have? Image separator, left position, top position, width, height, a reserved, which we can just ignore, size of the local color table, I think whether there is a local color table, interlace. So we need this information for processing, but not super interested right now. If we look at the bottom here, we copied out the grammar. So a graphic block, which is what we must be on, because it starts graphic control extension. We didn't get one of those. We got, what did we get? We got an image descriptor, which may be followed by a local color table, which will then be followed by image data. So if we have a local color table, we have to read that. So we do care whether there is a local color table. Fine. So const local color table equals so const has local table is going to be the packed bytes ended with 0x80, because that is the most significant bit is turned on. So we end packed with that. If the most significant bit is turned on in both, so and, then we'll get just that one bit out. So it will be equal to 0x80. So we get a Boolean value. So if we have a local color table, then we want to know about it. For the purposes of moving on with the stream, though, if we don't have a local color table, we can just ignore it. So I just want to see if this image has one. Has local color table is 0. Awesome. So presumably the size of the local color table will also be 0. Well, let's just have a look at packed. So here, when we do this, we can look at the value of packed. But instead of just looking at it like that, we do to string 2. So give it as in binary. So we can see that bit number 4 is on. That seems a bit weird. So we've got 3 bits here at the bottom, which are the size of the local color table. And those are all 0. And then before that, we've got a 1. That's in the reserved space, which means we ignore it. Okay. Oliver Dunk is asking questions about GIF. Is it a good file format? It's so-so. I mean, I've looked at a few things, and some of them seem very cleverly put together, and some of them don't. This is sort of middle. The worst format I've ever looked at is zip. So the pkzip format. I wrote a decoder for zip files a few years ago, and that's awful. But then, I mean, that was written by one guy in like 1987, and then just more and more and more stuff was just added to it over time. It's got tons of like optional features. Like it has, instead of saying, oh, this thing should be writable, it has, hey, this thing is a Linux file format, and so it has Linux permissions. Oh, this one's Windows format, so it has Windows flags for readable and writable. It doesn't try and have a device-independent way of doing anything. It's got things for HPFS and various, all sorts. Every file system has its own way of baking information in. which is ridiculous. And things can be compressed or not compressed, and there's multiple different compression methods. They can be encrypted. They can be 32-bit or 64-bit. It's a file format that is just horrible, and there are things that just aren't specified properly. There are things that are just like, hey, implementations might do something there. Yeah, it doesn't sound fun. That should tell you about the there's a bit of lag between here, so yeah, sorry if you say something, it will be a minute maybe before I answer. What is a local color table? Okay, so in the spec for GIF, we looked at it a bit last week. So GIFs are not true color images. A GIF can only have up to 256 colors per logical image. So GIF can contain many images. That's how animation works. Is it has many images throughout the file, but each individual image can only have 256 colors. And you can save space in your file if you use one color table at the beginning of the file that says, here are all 256 of the colors that are used in my file. These are the only ones that are used. But if during your animation the 256 colors you picked at the start are no longer most appropriate, you can have a new color table for each sub-image, so you can have a different set of 256 colors. So that's what a local color table is. It's a palette, basically. It's the palette of colors that can be used to draw the image. This file format was originally written in 1987, so it is written at a time when using 24 or 32 bits of color on a single screen at once just wasn't possible. It seems a little antiquated now to do that. Does the new color table persist from then on, or just apply to that frame? Just to that frame. There is actually, I think the global color table and all of the local color tables are optional. There is actually something in the spec that says if the program loads a GIF and it has a global color table, then the next GIF you load, if it doesn't have any color tables whatsoever, you just use whatever you previously had. There's not like a standard one that you can use. It's just if you load two GIFs, one after the other, and the second one doesn't have any color information, you are supposed to use color information from the GIF you processed last time. Madness. But no, that doesn't apply within a file. So if you have a global color table, it will only be used where there isn't a local color table, and similarly, if there isn't a local color table, it goes to the GIF to the global color table, not to the previous local one. So we'll only ever have to store. We'll have one sort of permanently stored color table, and then for each sub-image, we'll have another one that we're looking at, maybe. Yeah, I don't think anyone in practice actually does that, where they send two GIFs, one of which has color information and then the one that doesn't, or at least not anymore. But apparently, back in the days of bulletin board services, that was a thing. That was just how it worked. Madness. So I'm not going to do this. So this looks like I'm getting to the end of here, and I have has a table is 0. So the next thing I get, oh, I know what's happening. So basically in here, so I've got a table, I'm looking at a table-based image. I've read my image descriptor. The local color table that's optionally there is not there. So now I should be followed by image data, but I'm not actually reading any image data. I'm just returning back up the stack. And so the program thinks that I'm after a new data block, and it's saying, "Hey, 255 isn't a valid block type." So at the end of here, now that I've read this information, maybe I don't want to return this. Instead, I want to read the color information. How big will that be? I don't know. So at the end of here, local color table followed by table-based image data. Oh, exciting. Okay, so the image data for a table-based image consists of a sequence of subblocks of size at most 255 bytes each, containing an index into the active color table for each pixel in the image. Pixel indices are in the order of left to right and from top to bottom. That's good. Each index must be within the range, the size of the active color table, starting at 0. And it uses LZW algorithm with variable length code, as described in Appendix F. So, subblocks. We do need the subblocks to actually return us information after all, because the same process here is used by the color information as was used for the data, the application data. So we don't want to skip at all. I need to put all that back. So this is going to be this dot reader dot get byte array length, and we're going to return the length and the data like we did before. And then up here. Now that said, we still don't actually care about the data here. So we don't actually have to pull the data out. This should still work. Yeah, we got to this point. So here, the image data. So I'm just going to put in like an assert kind of thing. So if has local table, then throw new error, not yet implemented, local color tables. Just that if we've got one later in the file, we can see where our bug is. We can see, oh, the reason why the next thing isn't parsing is because it's a local color table and we haven't dealt with it. But otherwise, the next thing that we're going to get is going to be a we're going to get subblocks just like this, only with data. And at each stage here, so we have subblocks. It's going to be an array. We're just going to stick things in that array. Subblocks.push data. And then at that point, yeah, okay, so what do we get? Subblocks. We got 493 subblocks, bytes, which are seemingly random information, but it won't be random. It will be LZW encoded image data. So what do we get? The LZW minimum code size is the first byte of each block. Oh no, it's not the first byte of the block, it's the first byte of the section. So the encode size is get byte, which in this case was 0. Really? I would have expected the minimum code size to be, well, bigger than that. LZW minimum code size. I was reading about the LZW file format, and basically, no, you can't have 0 as a code size. that just doesn't work. That means that the very first thing you read, you'd read 0 bits, and that will tell you what the first value is, and that doesn't make any sense. Image data for a table-based image consisting of a sequence of subblocks of size at most 255 bytes. Unless this byte determines the initial number of bits. So as described in Appendix F. Let's find Appendix F. Appendix C, Appendix E, Appendix F. Variable length code LZW caption. Here we go. Establish the code size to find the number of bits. Establish the code size. The first byte of the compressed data stream is a value indicating the minimum number of bits required to represent the set of actual pixel values. Normally this will be the same as the number of color bits. Because of some algorithmic constraints, however, black and white images which have one color bit must be indicated as having a code size of 2. So we're expecting it to be 8 because there are 256 colors. That's an 8-bit value. And we did actually get 8 as our next value. Oh no, not as our next. As the next but 1. So what am I doing wrong? What am I doing wrong? Image descriptor, local color table, image data. No, that doesn't make any sense. Is there something at the end of the image descriptor that tells us what the is it followed by some other byte? Or do we get a length of what this should be? No, this is a fixed length. This is clearly a fixed length. Well, that's annoying. So what's my bug? What is my bug? We don't have a local color table, and then here, well, let's step through it. Let's step through it and see what could be going on. So we read a byte for the minimum code. Oh, hang on, min code size is 255. Oh, okay. That also seems wrong. I'll be honest. Does it? Okay, so it's not in bits, it's in number of values. We're okay. We're okay. I was already reading it off the front, so that's why it's not in here. It's not in the subblocks. Phew. So now we get to do an LZW decompressor. Have you got any parsed data to use as references? Are you blind until you output something? I could. Some might say should have got some reference data, and I didn't, because I'm not very clever. So we're just gonna have. I'm gonna be blind. But you don't have to be. I mean, in the example stuff here. So, in the Wikipedia page for LZW, Lempel Ziv Welsh, after the computer scientists that invented it, there are some examples, but I haven't been through and made these into files that I can like load up and test with. So I'm going to be blind, but I like that. I like the ambiguity. I like not knowing. I like not knowing what I'm doing. If I don't know what I'm doing in these kinds of situations where I deliberately make myself not know what I'm doing, it makes me feel more comfortable when I should know what I'm doing and don't. There you go. So we're going to make a new class, which is an LZW decoder. And this is going to take a this is going to take one of these readers. It's going to take a buffer reader. Because I need to be able to read data out of the stream. Start reader equals reader. Now LZW decompression is read. It's clever, but not super complicated. So the idea is that you have, when you get given some data, you have a dictionary of possible values that is defined by your application. So in GIF, your possible values are 0 to 255. And somewhere in here it should tell me that some of those codes mean something different. They're not. It's not just the colors. I'm not explaining this very well. So this tells you how to do it. How to do the decoding for GIF particularly. So okay. So what happens is you have some data and it is made of bytes, and you want to compress it. So what you do is you start by just saying, hey, this byte is going into the output, and there's nothing special about it. But instead of saying that with 8 bits, let's say we'll talk about the fixed width code version, which is use 12 bits. So you use 1.5 bytes. And if those first 12 bits, you take them out and you parse them as a number, if that number is within the size of your dictionary, of your initial dictionary, so in this case 0 to 255, then you just use the value as is. So if I have if the first 12 bits that I read gives me a number of 0, then in the output I just put a 0. I just put a 0 because that's the result. And obviously just doing that is going to mean that the file takes 1.5 times the space. That's not compression at all. We're rubbish. What you do is then you take that first value and you also stick it into a dictionary. Okay, not the first value, but when you read the second value, you take the first and second values and stick that in a dictionary. And you give it the next number up as a code. So we've got here the largest code is 255. So we set in our dictionary that value 256 is whatever the first value was plus the second value. And then later on, we could read a code that says 256, and we say, oh, well, we know what, even though it's not one of our original bytes, we still know what it is. It's in our dictionary as index 256. We can load it up, and it'll be those 2 bytes. And as you go on, when you load up something that is multiple bytes long, you have that as your current string, and then you say, okay, and when you create the next dictionary item, you take the first byte of that, and you grow the size of the string again. So you can take a long string you've already got, make it even bigger, add that into the dictionary. So in here you can see, in this very simple example where the string is to be or not to, to be or not to be, or to be or not, whatever. You can see the dictionary starts off as just the 26 alphabet characters plus this, which is they'll be using as a clear code, which we'll get to in a minute. So the dictionary is originally just the 26 alphabetical characters. And you see that you read in a character. The current sequence is nothing. and we don't do anything with it. Then we load in the next one, and we can see that the thing we'd already read was a T, so that's going in our output. The next character is an O, so we output to the stream a T, but we add to the dictionary TO in the next position, 27. Now our current character is O, our next character is B, so we output the O to the stream and we add OB to the dictionary. And then later down here, our current character is T, our next character is T, we add that. Oh, so yeah, so here we load up our next value and it's actually already TO. We've loaded up TO because we got the code 27 here. Our next code is 27. And so we can now concatenating the TO that we already got with the B that we get next to make a TOB in the dictionary. And you see the dictionary, the values get bigger. And you keep adding things to the dictionary and then using them until you've processed the whole file. And this means that by the end of processing a large file, you have this large dictionary of things to look up, but you didn't have to send that large dictionary in the file. So both the encoder and decoder can agree on what this large dictionary of lookups is without having to transmit it over the wire, so saving you space. With variable width codes, you start by saying, okay, I'm actually going to use 3 bits for my codes, so I can only have values 0 to 7, which means that your initial dictionary is just the bytes 0 to 7. But then when you get to a point where you're adding the next thing you add is going to be index 8, then you grow the size of the code, and now everything is an 8-bit. Is a 4-bit code, and so the encoder and decoder have to make sure they're in lockstep. So the next time you read 4 bits and decide what the number is, until you get to having 16 things, and you're going to add a new thing to the index, and now everything's a 5-bit code. So now you have to read 5 bits every time, even for a small number. You always can kind of something you have with 1 extra character. I believe it is always with 1 extra character. There's another way of doing it. Okay, so my example, I was looking at the encoding where you're just building the dictionary. The decoding, this is why it didn't quite make sense. So you're reading in these bits to decide what the next sequence is. And in fact, here you can see this is where the code is getting bigger. So this is 1, 2, 3, 4, 5 bits. At this point, we go up to 6 bits because we created 31, which is the last one that could fit in 5 bits. So from now on, we have to read 6 bits a time to work out what the next number is going to be. Oh, sorry, that one's still 5 bits, but this one's 6 bits. So there are slightly different alternatives to this, where you're not just adding the first character, but instead, if the next thing encodes a string, you actually can concatenate both full strings. So here you read in a 2 and a B, and you add in a TOB, whereas you could have it add in a to be, 4 characters long. I believe that one actually adds in the TOB and the TOBE as separate indexes. So your dictionary grows much quicker, which may or may not be good for compression, depending on what you're encoding. Your dictionary can eventually run out of size, and then at that point, you have to send a clear code which says get rid of the dictionary and start again. It can't grow forever, but you might still need it to have new things in later. So at any point in the stream, you could get that clear code, which will say, I need you to just get rid of the current dictionary and start a new one. So you'll go back to basically reading 1 byte at a time. and not having very good compression. And the compression will get better and better and better until you fill up that dictionary, and then you start again. So this means that when you have a common sequence of bytes, of colors in this case, this should be compressed very well. So our somewhere in here we have the actual algorithm. Oh, well, you know what? GIF also gives us the algorithm, or most of it. Package the bytes. So this gives us some extra information, because LZW doesn't fully specify everything that can happen. It doesn't tell you what the it doesn't say whether it should be variable length or fixed length codes. It doesn't say what the initial code size is. It doesn't tell you what the clear code should be, or even if there is one. So GIF then has to give us that information, and it tells us that it's variable length code, variable length encoded. It tells us that we need to output the initial count. Well, if we were encoding, so in the file, the initial code size is specified there already. End of information code is defined explicitly indicated at the end of the image data stream. Indicates the end of LZW processing terminates when this code is encountered. So we have a clear code, a special clear code, and an end of information code. So when we get the clear code, that tells us to reset all the parameters and restart the table. The value of this code is 2 to the power of code size, which makes me even more sure that 255 is not a good code size to have. Min code size 255. That feels wrong. But I don't know what I've done wrong to get there, because this image width and image height seems good. Maybe. What is the size of our image? Where is our image gone? 480 by 480. Oh, okay, maybe. So maybe I'm just reading something wrong here. Maybe this shouldn't be a. Unsigned, 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 unsigned. Separator. Oh, our image separator was a 0. And it shouldn't have been, right? Our image separator. Oops. Should be a not x2c, which I think, if I'm not mistaken, is a comma. And there's a comma. We didn't get that. Oops. So what happened? What happened? Why did we think? Oh. Oh. Yeah, I forgot to show the example GIF that I found. So I think I know what's happened. Is that here, I'm already parsing that first byte. I'm already parsing that first byte, which is the separator, the comma. So I should not parse it in my code down here. Oh, and then I'm doing something there. So that seems wildly wrong, but in a different way. Like this width and height seem the same, and we know the image is square, so that seems good. Our top and left are now both 0. Our packed byte is now 0. It doesn't have that 1 in the reserved position, which seemed weird before. Has local table is still 0. And our min code size is 8, so 8 bits. Perfect. And because of that, because it's 8 bits, we know that when we read 8 bits, we're going to get a 0, and then we're going to get a 1. So these are going to be index 0 in our palette, and then index 1 in our palette. And in fact, until we until the dictionary gets up to being bigger than 8 bits, we won't actually be able to get any code that isn't directly just in the palette. So if we drew this just as is, the first few lines of our image might actually just look right, which is something we might test in a bit. But you see here we've got these two values which are the same but are clearly wrong. Our image is 480 by 480. That is because if we go into here where we're doing a get u16, so let's get this result, and it says 57345, clearly wrong. If instead of doing this, we could use get u16 LE, no, I need autocomplete. Get uint16. Oh wait, hang on. It's a comment. So true. Oh no. Just need to get rid of the LE. 480. So basically, we were reading it as a big endian number, and it needs to be a little endian number. So in here, we just need to pass in a true, because apparently GIFs use little endian. So now when we run this, we get image width 480, image height 480, which seems much more reasonable. Cool. Okay, so just as a test then, let's go ahead and get ourselves a canvas. Something we've been wanting to do for a long time. I'm just going to stick this in here. Canvas equals document. Stupid room lights. I'm in here still, just because I'm not moving. But create element canvas, and we'll get a context on that canvas. Type context equals canvas.get context 2D, because we're not gonna WebGL this. I think that would be excessive. And then further down here, when we load in the information about our document.body.appendChild canvas. That won't actually work. The body isn't closed at this point. We'll do that here because we'll have awaited a bunch of stuff. That is not how we should do it. We should be using what happened? We should be using like onloaded or something like that. Yeah, luckily these lights dim slightly before they go off, so you get a little bit of warning before it goes pitch black. And obviously my face is not the main thing that you're looking at here. So later on, when we read the width and height, I'm going to go ahead and change canvas.width equals this.width. Obviously, this isn't how we want to do it in the end, but I want to get to writing something out here. Canvas.height equals this.height. Why do I have two windows, and why won't you show me the other one? Oh, there we go. Let's put these in here. So in the body we have a canvas which has been sized correctly, and then here we're going to get so our color information, which we already read out, we read out as, so where is it? Get global color table. We're just reading out the size. Interesting. So we're going to take the context of the canvas, and we're going to get image data 0 0 this dot width, this dot height. And what is that? Oh, dot data. Oh no, can't call that data. That is image data. And then how do we want to do this? No, let's not mess around with image data. That is more, it's the proper way to do it, but it's more complicated. So what I'm going to do is instead for let I equals 0, I less than size I plus plus. I'm going to read from this subblock. I'm going to say, and I'm going to draw to the canvas. What are we expecting to see at this point? Junk. I expect to see the right thing for the first line, maybe, and then it should descend into junk, because we haven't decoded it properly. But the nature of LZW is that the first line, the compressed version and the uncompressed version should be the same. That's my understanding of the file format. I might be wrong. It might be that it immediately goes into 9-bit codes, and this will it'll all just be junk. But I want to let's visualize the junk. So we need to maintain an X and a Y, and in fact these should be here, and image top position, and what we're going to do is if X is more than image width, so we're gonna scan along and draw things out as we find them. Yeah, and basically we're just going to be reading a linear array of values. So we know that at the beginning, x equals 0, y equals 0, byte 0, fine. But we're gonna read along, and eventually we're gonna get to a point where we just carry on reading this in a line, but we'll have reached a point where the x value is wider than the screen, and so we need to start drawing that on the next line. So that's what this is going to do. So we're going to say here x plus plus to move it along. But if the x is more than the image width, if that puts it over, we're going to go back to the beginning. And if y is more than image height, then we're done. Break. Even though we'll probably have data left to read because we're not decoding this properly. And then in here we're going to do context dot draw, not draw image. Fill rect. Sorry, fill rect. And we're going to do it at x, y, and it's going to be 1 by 1. Before that, we just need to set context.fill style to be. And what we're going to do is we're going to read out the hold on, I plus equals 3. I actually don't know what the image data is like. Is it the color palette? Global color table. About color tables. Oh yeah, we did look at this last week. It was literally just RGB, RGB, RGB. So about color tables. Global color table. 3 to the power, 3 times 2 to the power of whatever the size was. Red 0, green 0, blue 0. So what we need to do is we're going to read a single byte. Yeah, we are reading a single byte that tells us the index of the color we need to look at. So our color index equals data I, and our color is it's this dot global color table. The red is it's I times not I. It's the color index times 3. So whatever the color index is, we need to multiply it by 3 to get where in the color table the color information starts. And this will be our red value. And then green and blue are the following bytes. Green, blue, so that's that plus 1, and that plus 2. This is not how we'll do it in the end, but it's a reasonable start. And then for the fill style, these will give us numbers between 0 and 255. And we have a way of dealing with numbers that way, which is the CSS, the way of doing CSS colors, RGB, red, green, blue. Do not recommend doing this for anything real, because you have to parse this string every single time. We have to produce the string, and then the browser has to parse it every single pixel. This will be horrible, but we'll find a better way in the future. I just want to see what we're getting on the screen here. Is it nothing? Context.fill style is not a function. You're correct. It is not a function. It is a property. Fill style equals. Ooh. Oh, but are we not getting anything? Why is this... Why isn't this working? This looks like it's actually disconnected from the... Oh, I have an infinite loop. Infinite loop alert. Infinite loop alert. So how about at the end of here... while size not equals 0, do I change the size or something? Am I already using I? Am I overwrite it? No, that doesn't seem right. Size is not 0. Doing I++. What's your problem? Oh no, just really slow. So that looks like proper junk. Proper junk. Yeah, so it wasn't crash, it wasn't in an infinite loop. It was just incredibly slow. Let's see if we can improve on junk. My mic is going fuzzy. Yeah. It was bad. It'll be this thing, probably, because we're doing it 480 by 480 times. And in fact, this isn't. No, we are setting the X and Y here, so it should be okay that it's gonna each subblock should start down the image correctly. But yeah, very slow, and I suspect even worse than that, it's going to be doing all of the images. My mic is still fuzzy regardless. Oh, unless that's a joke about fuzzy mic. I don't have a fuzzy mic. I have a borrowing this thing, which is not fuzzy at all. Shiny. Oh my goodness, 20 minutes to go. We have something on the screen, but it's terrible. So what I'm going to do is here, I'm just going to throw new error. Because one of the other things that will be happening is that it will be going through every image. Oh, no, it sounds very bad ever since we loaded up the page. Ah, okay. I wonder if YouTube has downgraded my bitrate or something. No, that can't be right. So we're reaching the end of here, and there was apparently nothing in the... Oh, we're not even adding the canvas this time. Why not? Gonna do it at the end of here. I need to do it earlier. So let me just okay. I'm just going to see if I can see if anything is taking up particular. So my recording software is taking up a lot of CPU, but that's about it. I'm just going to assume all is fine. Okay, so there you go. That's much faster than it's doing just one, and obviously it is still junk. I mean, if I can zoom, can I zoom this in? Where's that working? So I think that right here at the beginning, it might be very slightly more structured. Like a slightly different color out there. No, that's me. That's me wishful thinking. So let's decode some data. So what do? The algorithm for here is pretty simple, as I understand it. Yes, I am using OBS. So basically, I need to read some amount of bits. So also here, I'm going to say what the initial code size is, because that's super important for the reader. So initial code size equals initial code size. Oh, well, no, this just the code size, because we'll change it, so it won't be the initial one all the way through. Now in my reader, I'm going to need to be able to read some... yes, I should probably use the supercharge set rather than doing this myself, ghetto style. But I didn't want to brand it supercharge because this is my own thing, sort of. I didn't want to have the pressure of needing to fill the high standard that has been set before. So if I'm going to be reading bit fields from here, I need to be able to read like half a byte. And I can't do that directly from the data view, so I need to be a little bit more careful here. So I need to be able to read part of a byte, and so I need to read a whole byte, use part of it, and then remember the next bit, the bit that I haven't used yet. So what I'm going to do is I'm going to say we'll start partial equals 0, but then I need a flag, yeah, because the partial like could be zeros. We'll start with has partial equals false. Stupid lights. So in here I can say get bits, how many bits I want. And then what I'm going to do is I'm going to say that I also need to know not just that I have a partial, I need to know how many bits of partial I have. So my current value, let's say that the number of bits I have. Okay, so while my bits remaining is less than the number I want, what I need to do is I need to say that this dot partial equals the current partial that I've got shifted up by 8 bits and ORed with this dot get byte. So I have my partial value, I move it over by 8 bits and stick the new 8 bits in front. And now my bits remaining is 8 bigger. So this while loop will run until I have enough bits in my partial value to cover the number I want to read. And now I haven't really thought about this. I'm assuming that that when the next byte comes in, I stick it in the least significant place, and I'm going to be reading my number out of the most significant bits. That might not be how GIF does it. I'll check that in a moment. But we'll carry on like that for a moment. It's fairly easy to change it over. So my result is going to be so I'll end up with a number that potentially has more bits than I want, but the extra bits, the bits I don't want, are all in the least significant place. So let's say I have 3 extra bits, then what I can do in order to get rid of those is I can shift the whole number down by 3 bits, and that will be my result. So I can then, well, okay, so the result will be this dot partial shifted down by this dot bits remaining minus number. So however many bits I have more than what I need, and I obviously need to return that result. And then here I say this dot bits remaining minus equals number, because I have removed them. And also that this dot partial equals, and basically what I want to do is, I actually don't need to do anything. I'm now saying I've only got, let's say, 3 bits. They will be the first 3 bits of partial. So even though I already have some data there, it will be ignored. No, it won't be, because when I shift this down, it won't shift in zeros. It'll shift in some of the data that has been stored there before. So I need to mask it off. So this dot partial equals, ampersand equals, and it's going to be 1 shifted up by this dot bits remaining. Minus 1. So let's say that this bits remaining was 2. So I take a 1 and shift it over by 2 bits. So I get 1, 0, 0 in binary. And then minus 1 from it. Sorry. Yeah, a minus 1 from it, and then I get just 1, 1. So I get 1s in the 2 bits that I want to keep, and 0s everywhere else. So when I AND that with partial, it basically zeroes out everything except the bits I want to keep. Cool. I have written code just like this before, so if I've got it wrong, I will be able to find it later and spot any bugs. Obviously this isn't doing anything. I'm not actually creating an LZW reader. No. LZW equals new LZW decoder. And I have to pass in the reader and the initial code size, which I don't know. That happens per image. It could be different for any image. So I get to do it here. I'm just going to, how's it doing? And then here, for each subblock, I need to not just parse it, but then decode it. So const decoded equals lzw.read. No. Can't read it off the stream. I've already read it. That data is gone. So I need instead to pass in the array buffer. That's going to have to be how it is. So instead of creating a new one with the buffer, with the reader, sorry, I'm just going to say what the code size is. And I'll read it, use it over and over again, so I'm using the same dictionary. Yeah, that sounds about right. So we don't take the reader. Instead, when we read, in fact it won't be read, I'll call it decode. gone? Stop decode. Which means that this bits stuff needs to go on the LZW reader, because I'm not actually using the buffer reader anymore. So it's going to go somewhere like here. Interesting. I don't know. This is not working the way I thought it was going to quite work. Right, well, maybe we're getting time when I said I was going to stop, and I think it would be good to stop then. I don't want to go on forever. It's just annoying. I have an image on the screen. It's just junk, though. And I wish we'd got a bit further. So basically I need to sort of redo this so that it can get bits from an array buffer, or I need to be able to have this, or my LZW decoder needs to be aware of how these subblocks work, where each one has a length and then some data, because it's going to have to parse that. It's going to find the length in the middle of a chunk of data that it's decoding. What to do? So I think what I'm going to do is call it there, which is annoying, because I would like to have got the LZW decoding in. It's a short algorithm. I should probably have started with this, but even before we got to using it, it's a fairly short algorithm. But what I'll do is I will open with this next week, and get this working. I'll work out in my head how I'm going to arrange this. I suspect that this is going to take in an array, and I'll just have to either get bits will take the array, or I have some new object. I could create a new buffer reader that works on the sub buffer, just on the buffer that represents the part I'm decoding. I think that's what I'll do. In which case, this get bits stuff can go back here, which feels a bit more natural. Okay, so here's what we're going to do next week. To do create a new buffer reader using the past in typed array. Stream bits out of that reader up to a given length. So we know what the length is that we can read for the data. Return a decoded array buffer. Oops. Okay, so that's, I think, what we can do. Feel free to ask any questions. I'll hang around for a few minutes. I see one question. Before you go, if you're allowed to say, what are you doing inside Google at the moment? I am allowed to say, because what I'm doing is basically public. I work in developer relations on the web developer relations team, and my job, my day job, is helping developers make stuff good on the web. I guess you could say that my current goal is make every website great. That's the grand scheme, the high level overview of what our team does. Make the web, make every site on the web be worth visiting. That's obviously a lofty goal, and the way we're going to do that is going through common mistakes and things that people aren't doing but can be done, and showing people how to do things properly. Is this GIF code going on GitHub? Yes, I failed to get around to doing it last week, but it will be, and once I've got it up there, I'll be able to just push it at the end of a session. I just need to create the repo and put in appropriate licenses and things. So hopefully by the next time I do a stream, you'll be able to see the code. This is obviously not production code though, so yeah, it's a learning tool. I should say that before anyone decides to take this as how they are going to actually decode GIFs. Let's get rid of that big comment. Yeah. Any particular projects at the moment? Not that I mean, technically it's public, but I'm not talking about it yet. So no. I'm working on media-related things. Let's say that capturing images and editing images, things like that. Which is why I was thinking about GIFs when I started this stream the other week, last week. Okay, so I'm gonna call that there. Thank you for watching. For anyone who's watching, thank you for watching the recorded video. Please feel free to leave comments. I'll try and get to them. My Twitter is @wibblymat, which I should probably make a card for, so I'll put it up on the screen now. That's @wibblymat on Twitter. Yeah, please ask me questions, and I will see you again probably at the same time next week. Okay, cheers.